വേറെടല്ലോ പോകുന്ന ഒന്നും കൂടി നടക്കല്ലേ.
So, welcome to Qatar. I hope you enjoyed the program so far. My name is Ehsan. I work as a scientist at QCRI.
കാര്യമില്ല.
I'm also working as part of the panel team in the last year that I joined QCRI. Also the Ph.D. team and also MenaML. So today I'm going to talk about transformer language models. So basically, like I switched a bit, like the topic that basically I would say kind of a little bit vaguely on listening towards another theory, which is my, I would say, area of interest. To be honest, like presenting transformers in 45 minutes, I mean, like I would say that like all concepts is very difficult, so I'm going to share like the kind of like the overview that I have, and I would be grateful to also hear your feedback. So I'm going to start with the definition of language. That's how actually I really start with things. So basically, like, of course, if you look up for a definition of language, you may see different definitions, like this is like kind of like the medium for communication and things like this. But one of the definitions that I really like is by Noam Chomsky, who defines language as a collection of sentences that they are built from finite set of elements, like sentences with like I would say finite length and from finite length. Actually, this definition was very useful to me because I was working on, I started my Ph.D. and I would say language modeling of protein sequences, and at that time it was kind of like a pre-AlphaFold time, so it was very difficult to convince people that there is a language, and I had a difficult time. Then I found this definition, and whenever people were asking like, why do you think there is a language for proteins, then I was just referring to this definition, which was simply actually satisfying. And yeah, I misused this definition, I would say a lot. But actually, one thing actually I like about this definition, from this point of view, many phenomena in the world can be seen as language. So, as I said, like biological sequences like protein, RNA, DNA, because they are like, I would say, elements that they are coming together, kind of like based on, I mean, one thing that is kind of missed in this definition is that this coming together happens through a rule, through like some, I would say, when we are talking about biological sequences, there is like a biophysical, biochemical rule that is dictating this formation of sequences. And about language is also the same. Like for instance, like when I was like presenting, I would say biological language modeling of biological sequences. People were saying that like protein sequences, they have 3D structure, right? So they are not like natural language. But if you look at natural language, it's also a 3D structure. So basically, we are limited in the time access when we are, producing sentences. But at the end, the words that we are producing, they are also forming kind of like, we can map it into like an n-dimensional space that these words are also, producing like n-dimensional, I would say, structures. So another thing actually with this, which also goes with this definition of language, is a theory in linguistics, which is distributional hypothesis. This one is also, I would say, the thing behind all these things that you can see, in the history of NLP, from, I would say, document term frequency up to transformers and large language models. So it's like, the thing that can characterize a word is like the surrounding. So basically, this is how even we define synonyms. Word. So like there is basically there is no, I would say, real maybe synonym for a word. How we define synonym is that words that can be replaced. So basically, if two words they have the same same context, we can replace them. That's why we call them synonyms, right? But you can try and you can see like not all those they have exactly similar, I would say, senses, so that we can replace them in all senses. But the importance of this, I would say, hypothesis or this, I would say, definition is like something that can contribute into computational methods. So, it has been proposed, I would say it should be even earlier, it's not only like by, I would say, non-linguist expert in 1950, but also by people before, I think it has been also proposed. But as I said, like the importance is in the computational methods. Since we can characterize a word by surrounding, we can use this principle to have computational models. So if we want to say, like two words, W1 and W2 are similar, we can say that we can reduce it to the similarity of their contexts. And so, as I said, like it has been kind of like the basis for other words. And actually, like this thing actually like characterizing things by its rhyming, again, it's not limited to the words in language. Like we can characterize people by their friends, we can characterize countries by their neighbors. So it's kind of like a thing that it is, yes, you can observe it in many, I would say, like the word. This is how it is designed, I would say. That's why actually I think language modeling is kind of applicable to many things in the world. And what is language modeling, like the computational thing? So, I would say, as you may know, language modeling is defined as assigning probability to like a sequence of words that you can use like a chain rule to like, I would say to write it. But the thing is that actually like with this, I would say, probability distribution, you can use it for in two manners. You can use it in many manners, but like one would be like to generate, right? You can condition and what has been generated so far and generate the next one. Or you can use it to somehow to, let's say, if you have two generations, you can assign different like probabilities to them to see which one is more valid based on the system. One thing that is very interesting about language models, and I think that's how it became very, like with the, I would say, growth in the computation and so on, it became more and more important, is that this probability distribution is kind of like a compressed version of the whole language. So it has information about syntax, semantics, knowledge, and everything in the language. And this view can also, of course, like criticize it with all these, like I would say, hallucinations that we can see in language models and so on. But that's a way of modeling, right? But like the language model itself is something that has, I would say, all this information, syntax, semantics, and maybe you can, for all layers of like language, you can say like from phonology to pragmatics. And there are different types of language models. They started from Engram language models that you have maximum likelihood based on like counting of Engram up to like neural language models that we are trying to learn representation from data. So one of the, I would say, successful models, pre-transformers or like contextualized embedding was like Engram. I think this model is also very simple, but it helps a lot like to see the concept of context independent representation for text units. Actually, like whenever we talk about like words, replace it with anything. Like you can replace it with like I would say molecular fragments. You can replace it with people. You can like anything. Like because as I said, this view of language you can apply to many things. And also, when you are talking about language, but I mean, like, I think this is always applicable, that whatever you see at the word level, you can go to character level and maybe even lower, like, I don't know, if you want to go to the word level or maybe another paradigm. Or I would say, if you go to like the sentence level, paragraph level, you know, and so on. So basically, the things can be applied like, you know, at different things. But one thing that is very interesting about this model is that what we are trying to do in this simple neural network is that based on a given like a word, we are trying to predict the surrounding, right? So based on distributional hypothesis, as you may remember, words that they have similar context, they are synonyms, right? So if we have for two words, we are predicting the same surrounding, meaning that we have the same intermediate representation, those words are synonyms, right? So basically, this architecture is using exactly. I mean, it's an architecture analogous to the language modeling, not exactly language modeling that's trying to predict like the surrounding from the given word, but it has somehow, I would say, high alignment with the distributional hypothesis, because we are trying to give the same representation to the words that they have similar surrounding. You know, like, let's take the word light. So the word light has different senses, right? So basically you can have the sense that is like, you know, the morning light, you know, like the light beam, or like this sense that is like something that can result in movement and fun. So basically that's one context. The other context is about like the weight. You know, this suitcase is very light and easy to carry, and the other one is like about some opposite of maybe something like intense or something like that. So these three senses of light exist. If we use this architecture, what we have at the end, we would have, you know, because we are not looking at so we are using the context, but like at the end, for all occurrences of light, we would have single representation. That is what we see in this hidden area. So if we visualize the embeddings that we are training for this word, it will be something similar to this. So the word light and all these similar concepts are at its running. So with this model, we are not distinguishing different senses of light, but we put all of them together somehow, right? So we have a cloud of this, like, I would say, concepts, and which is also, I think, it's a very nice representation, because we see all the senses of the word in this representation. But it doesn't have, you know, it doesn't distinguish between like the light in the morning light or like this light suitcase, right? So, yes, please.
So we have the projection embeddings on the right side, right, for the
Yes.
graph. So what are we actually plotting? So what is x-axis and what is y-axis? And who's also deciding these embeddings? Like what is going to be next to each other? And then based on this, we do calculate the Ehsan similarity, right?
Yes.
So yeah, who already created this space and how it's being decided?
Sure. Thank you so much for the good question. So basically, you know, like, how this, I would say, skip-gram network, or like, I would say, this view is like, I would say, it's trained is like this, that we have, let's say, let's take like, I mean, Wikipedia, right? And then all context of, you know, basically, you would have, let's say, for certain window size of, let's say, 5. We get all windows of size 5, and we would have, let's say, a word in the middle, and we are trying to predict the surrounding word, right? And we start with very naive representation, which is like one-hot representation, meaning that if you have n vocabulary, you would have a vector size n, and train this network that we are predicting from the word in the middle, the surrounding. After training and backpropagation and everything, so we would have this layer, right? The representation of each word. If we fit this network with the word, we would have this representation in the middle. I'm a bit simplifying, but it's kind of like so. We would have the representation in the middle, and then it would be so based on the sizes of like this network. Let's say if the size of this layer is 300, for each word we would have a vector size of 300, and then you can use like let's say PCA, PCA or any projection, and you put those vectors into the 2D space. And then since the word, like the surrounding of like I would say, like for instance we can see here light is close to suitcase, it's like to TV or something like that. So basically based on that, these embeddings come closer, so basically it's happened through the training that these words and these vectors, they form their neighborhoods somehow. Yeah, so basically one thing that I wanted to emphasize here is that here the specific context of the word is not present, right? So for the word light, you would have representation like this surrounding, so basically like kind of like a neighborhood. It's not exact representation for the let's say the context in terms of weight, right? And that's how actually I would say first lesbian models like language models that we're using that I would say time series they came in place to add the contextualized information. So basically through the states we kept like what is the context of this like light, and then as you see like there is a suitcase, then it's somehow disambiguate. What is the embedding of this form? But here we want to focus on transformers. So far it was kind of, I would say, the introduction, like how the field moved from, I would say, somehow like the definition of language, the distributional hypothesis, up to like this point that we want to have contextualized embedding. So that when we have the word light, based on the context, we have an embedding that is context, I would say, dependent. So how it got in the big picture is like this. So, like here, like the transformers, they have different angles, and like, there are researches on, let's say, positional embedding and the attention itself, it has its own, like, I would say, stream of research. But here I want to just focus on the big picture and mainly attention layer, or like, let's say, attention in general, that is the core in the transformer architecture, and maybe a bit like the discussing in details, and then I think we can follow up this maybe I'll go all in node and the other systems, right? So let's say we have these three senses for the word light, and then we have the transformer, or the core of transformers again is like the attention. The rest are, with an exception of, I would say, positional embedding that we also talk about it. Like, we will talk about it, the attention is the core. So basically, we have the embeddings of the words at the input, right? And then we have this attention, and then we have, for each word, we have like an output embedding. But the difference between the input embedding and output embedding is that the output embedding is contextualized. So in the input, we have something like similar to scriptgram. The word light with all senses encoded into like a single vector is not disambiguated. If you are talking about light as in the light joke or like light in the light suitcase, right? And in this layer, with the use of this layer, we disambiguate. So the output is something that is already disambiguated. But how we do it? So here we focus on the attention, and we start with the, I would say, general form of attention. Here it's specifically self-attention, but we talk about trust attention, which is like the general form, and then we jump into self-attention, which is like so in the what we have in the we can look at the trust attention as an operator, right? So similar to the convolution operator, like the current operator, this is also like an operator. And what is the input? The input to the attention is a query and key and values. But what are those? So let's say you have like, let's say, a question for just like a query vector, and it can be just one. Let's assume that it's just one word. It can be like a sentence or anything, but like let's assume that we start from one word. So let's say it's like the word dark, so we have an embedding from it. The embedding can come again from, let's say, sticker, right? And then we have the whole sentence, which is like the morning light filled the land. So, and these are our keys. And what we want to have at the end is that we want a representation for the query that is kind of like contextualized based on this key vectors, right? So basically, and how we do that is that we define somehow, like let's say, the output based on the relevance of all these vectors to the query, and after having this relevance score, we do the weighted sum. So basically, as you see, like for instance, the word dark, we calculate the similarities. So maybe it has similarity to the morning, it has similarity to the light, and also one thing that you can also see here is that in the, I would say, in the space of like, I would say, representation, naming for words, and like how we define synonyms based on the context, synonyms and antonyms are very close, right? So because like you can always replace synonyms and antonyms as well. So like you can say this was like a good thing or a bad thing, right? So it's like these words we can always replace. That's why actually you see all these things that antonyms can be also replaced. And so as you see, like these intensity shows that the dark and light have high similarity of vectors, and morning and dark also a bit, and the rest are close to zero, right? So this is the relevance of these key vectors to the vector dark, which is the query. And then what we do, we just get the weighted sum of these vectors, and the weight comes from this relevance, right? So, and this is like how we have attention. But this is like the query and key. Let me just hold it and then. But like if we want to be more accurate, we use the key vectors only to calculate these weights. But what we are getting, for the summation, the vectors that we are using for each word are the vector, like the value vectors. So basically, through the dot product of, let's say, this vector dark and like these words, we calculate these weights, and then we use like kind of like another representation of these words, which are the value vectors. We get the summation. This is how like the, I would say, trust attention is in the general form. Can you guess? So basically, one corner case then we use like key vectors for the value vectors as well. So we don't have any, we don't distinguish between, like, I would say, value vectors and the key vectors. So that's one case. But in a general form, there are cases that we need value vectors to be separate. Can you guess, can you find some applications for it? When can we have, or when do we need to have another, I would say, value vectors other than the key vectors? So you know, like, since we are calculating, yes, please.
Language translation.
Yes, translation can be one thing. So basically, you know, like the vectors that we have, like the query vector and the key vectors, they have to be in the same space, right? Because we calculate the similarity. But when we calculate these relevance scores, then we can use any vector, right? The value vector can be in another space. It doesn't have to be the same space as like the query, right? So one way to do, so for instance, if like the, you know, when we want to have, let's say, this is like in English, but like our value vectors can be embedding of words in a multilingual space, or like in another language. So we have kind of like an alignment, and we calculate the embeddings that is like in another language. Sorry, you wanted to say?
So I was going to say the probability of next word and the recommended.
Yes, but yeah, I mean, like in general, we can use it for the next word prediction. But I'm just saying that in, what is the use of distinct value vectors than the key vectors? You know, just this is different. Yes.
However, I think there should be a link or a projection between the two languages in order to do that.
Yes, of course, it has to be. But you know, like we can have the output of first attention in another space. You know, in a different space than the original space of key.
But this projection or link between the two languages, is it learned or is it fixed earlier?
Yeah, I mean, in different settings it can be different, but you know, the concept allows for this, you know. So basically, here we can also use multimodality, right? So it can be the case that we are just calculating the similarity of like the natural language text, and the embedding the space we are using for the values are like the audio, let's say, embedding, right? So we have the output in the audio space. So that's the power of using like different value vectors. So some questions that maybe like, you know, just to yeah, I would say to recap what does like the first question. So can someone describe what is the how like the query and value and output are related to each other? So what are we calculating as the output? Yes, please.
So what I understand is that query vectors, like values are the enriched version of the query vector, and
Yes.
they are enriched using the key vectors and key vectors are generated from the sentence. So that's what I understand.
Yes, exactly. So we are transferring like the query using like the somehow like the I would say the key as like, you know, kind of like the key to go to the like I would say value space. And another thing is that, you know, why do we use like the softmax here? So basically like this is like the formulation we didn't talk about. So basically when we have like a query and then like the key, so query vector and the key matrix, right? And then we get the softmax to have like kind of like the distribution here. But do you know why do we use softmax, or like what is why do we use like just some summation?
Probably to have
Yes, and another point I think I also have.
To find probabilities of each token.
Yes, that's that's true. So we are going to like the probability distribution, right? So basically, this let's say the product can be also negative, right? If we maybe just have the summation, we would get rid of maybe some weight. So basically, like we are trying to also have it non-negative and also make it as a probability distribution. And then we have this this like term, right? Square root of d. Do you know what's d here? It's a dimension of vector. You know, like for instance, if the query and the query and keys, they should have the same dimension, right? The dimension is d, so that's like how we divide it. And I think next question is about that. Yes. So can you guess why we divide it by square root of d?
Normalization?
Yes. Is it random? So can we divide it by just d or d to the power of 2? So, I mean, at the end, it's also based on some assumptions, but unfortunately, the click doesn't work yet. Yeah, so basically, here so if you read it like the paper attention is all you need, this is something in the footnote. So most probably like, I mean, many people just saying that it's only for the, let's say, just as a like a weight, but I mean, there are some kind of, I would say, reasoning behind it. So basically, we are assuming that the query and key vectors are unit, are zero mean and unit variance. So that's why we can calculate like the mean and variance. The variance would be like for each would be d, and then since we are doing summation over all dimensions, the variance would be d, and then we do like just this for normalization. So this is minus 0 and square of like the variance. So standard deviation. Another thing is that, okay, and how do you think we can, like let's say we have a sentence and we have multiple queries, what is the efficient way to calculate for multiple queries like the cross-attention?
Multi-head attention?
Yes, so we can make it as a matrix. Instead of having just vector, we can have a matrix and then we calculate the matrix form. So this would be like the matrix form of it. And then the last question is that, so basically this way, when we calculate the similarity between query and key, we are capturing like the similarity between two vectors, right? But do you think two words, they have only one aspect of similarity, or they can share multiple aspects of similarities or dissimilarities? Let's say, I don't know, let's get two words, let's say, I don't know, softmax and normalization. Do they have, can you define some degrees of similarity or some aspects of similarities between them? So, it can be like this.
I think we'll put the summation of it before.
Sorry.
But max on the out, the summation B1. So the normalization
Sorry, maybe I didn't convey the question. So basically, the question is that this way that we are calculating like the similarity between query and key, we are arriving to a single score, right? So it's just like let's say scalar value, right? That is how this query is similar to like a key. But is it sufficient to represent the similarity of two words? No, two words can have different degrees of similarities. It can be the case that we are looking at their part of the speech tag, right? So that two words are nouns, so basically that's one similarity. We can look at their sentiments, that most of them are positive or negative. So basically, words, they share different degrees of similarities. And to address that, one approach is like multi-head attention. So we try to have multiple projections. You see, like we can have multiple heads, as you see, like this in this eye here. So for query and key and values, we can have different transformations, and we can have multiple heads. So the output would be concatenation of all outputs, and then also like the transformation of it. So this way we can address multiple degrees of similarities among elements at the input. So just to so this was like what we observed was like the cross attention, and one I would say a special case of it is like self attention, when the keys and when the query and the keys are the same. When you have a sentence and you want for each word to have a special representation based on the sentence, right? So the same as your colleague said. So basically, when we have cross attention, we are trying to have a representation for the query. And if the query are the words of the same sentence, we are trying to have a contextualized representation of every word in the sentence. So this way, we are trying to, let's say, if we have the word light in this sentence, then based on the surrounding, based on the contribution of other words, we can decide, we can disambiguate this everything, right? Because then we see that, like, for instance, the word morning is also there, and based on the embedding of morning, we are disambiguating this embedding that it's not the light that has also about heavy or suitcase or anything, but this one is about the light as like the lamps on, and like something that has like the basically and so basically like then this is how self-attention is defined. So basically like the query and keys are the same. Of course, it can be also similar to values, but we can always also distinguish as well. And one of the good points of attention is that we can have long dependencies, right? So basically, we don't have the problem of vanishing gradients, but the attention can attend to every part of the sentence. Okay, so this is actually the core in the transformer. If you understand multi-head attention, and so like just like another thing is that in the self-attention we can have also multi-head attention, right? So basically, so we would have again transformation of query and key and value, and then we can have multiple transformation and put them together. But one quick question: do you think we need different transformations for the query and key or not? Because we are trying to get multiple views on the similarity of query and keys, right? So if we are doing like a transformation of them to see different degrees of similarity. Similar to say you can get if something is like noun or sentiment or different aspects that can be learned. Do we need to have distinct let's say transformation, for query and key, because they are elements of the same sentence, right? So basically, we are applying it to the words in the same sentence. Do we need different Yes, please.
I think we don't need them, but each of them can attend to different part of the sentence. That way we can learn different representations.
Yeah, so we don't need, as you mentioned, but the thing is that if we do so, our attention diagram, so basically like if we see how different words in the sentence are and you know, like for this is given ahead, right? So just transformation of like let's say WI for queries and keys. This matrix becomes symmetric, and we are if we use the same WQ and WK, then our attention matrix becomes symmetric, and then we are not using all parameters that we have for to learn. So basically, we are just somehow it's inefficient for the training. That's why actually it's better to have non-symmetric. So basically, the attention from word, let's say, when the word is like you know, like let's say the word like is query to morning is different when it's like the morning is the query and light is the key. So we want to distinguish these two. That's why actually we would use different transformations for query and key. So you know, just to try to a bit dive into, I would say the architecture for the transformer, like mainly like the cross attention, but the rest are like I would say kind of like technical things or like engineering things, I would say. And so basically in the transformation block, the multi-attention, so basically we have the input. Please also take this one very serious because like pre-processing is a very important step, tokenization is a very important step. And then we have positional embedding. Positional embedding is also very important. So because as you saw in the you know, like what we were saying, we are not focusing on the word order. So basically the attention looks at all words at the same time. We are not distinguishing between the first word and the last word. So we need somehow like the order. So you know, like you know, for instance, let's say if you have a sentence that he eats the apple, or if the apple is, you know, in this case, I mean, if you put names, then like you know, the order, changing of the order will change the meaning, right? And so that's why actually positional embedding is also very important. And then we have at the core, you know, like the multi-head attention, and then we have the residual connection and normalization and so on. So basically transform that Sarah already gave a nice talk about it, and like so that it can improve like the you know, prevent the vanishing of the gradient, and we have the residual connection and so on. So but the core is these two, I would say. You know, the rest are I mean, there are also some I would say interpretable things here as well, but like yeah, so basically these two are the main things. What about the positional embedding? I think positional embedding is also very interesting research area that can be also explored more. So you know what we have for positional, I mean, positional embedding in the field has been also like it has also its own history and its own I would say research track. But one of the things that also came with this paper of attention is all you need is like this sinusoidal positional embedding. So basically, it's an additive positional embedding. It's like a dimension. It's a vector in the same dimension as our input vector, but it is in a way that so basically this similar or close positions, they would get this similar embedding, right? So basically, if you get the dot product of positions, we would see a matrix like this, right? So basically, you know, words that they have similar neighborhood, so basically they are like, I would say, they have high similarity. And it's kind of like additive. It's a bit like, sounds weird, but you know, like, just assume that if you see it in a way that when we have dot product and it is added, then this projection of them would also show up, and I think then it makes sense. So, and it's, as I said, it has its own research track. So basically, it can, so there are like linear positional embedding, there are rotary positional embedding, and I would say you can modify the attention mechanism. You know, like basically, we talked about cross attention as a like a very very general thing, or we say the vanilla cross attention. But the thing is that this attention is quadratic, right? So basically we are looking at the attention of all parameters or all elements to each other. But we can make it more, I would say, compressed, or we can make it more efficient. So there are attentions that you know, like only words that they are in the same neighborhood, they attend to each other. There we can also use the positional ability somehow to incorporate like this locality. So it's not only like about absolute position, it can be relative position, and it can be also incorporated in the attention for you. I mean, just to know that there are some research on this going on, so we don't have time actually to discuss all this. Another thing is like the layer normalization. These are actually, I would say, the engineering before, so the batch normalization we have for the, I would say, for the vector, but here we can have it for across features. So these are actually, like, I would say, engineering that contribute to like more stable training. And just to, so basically, this is how I would say, this will be somehow, like I would say, here we can conclude about the transformer architecture as a whole. But there are three variations of the transformers that, or three categories that I would also state as a, like a different architecture based on the attention. You know, like we have encoder models. In the encoder models, the attention is bidirectional, right? So everything can attend to everything. We have decoder models, the attention is unidirectional. You can always like looking at the previous words, right? And then we have encoder-decoder that we have two models. One that is like an encoder model, and the other one has cross attention. So it's not attention within the model, between like the red in the encoder-decoder model, between red and blue is cross attention. You know, so here we are using like the self attention, this part, and here we are using cross attention, and also in a so basically in a unidirectional way. And so basically, like an example, so like the illustration for the encoder and decoder model, I would say are kind of like identical, because it depends on how we have the causal attention, you know, looking at only previous words or not. But the only difference, is like is the direction of attention, and the for encoder model where transfers and other variations are examples of encoder model. For decoder model, GPT, llama, and so on, or decoder models that we have causal attention. We always predict the next word, you know, like representation. If we to represent a word, we always look at the previous one, not the next, not looking at the future. And then encoder-decoder models, they are also very powerful models that, so basically we have, as I said, like two models, so this is like an illustration of encoder-decoder models that, like, let's say we have a very large model, like encoder model that is with cross attention again, is connected to the other model. These models are usually used when we want to have an understanding of something and then generate something. So basically for the summarization, for translation, that we always look at, we need to look at the whole history. These models are very powerful. T5s and bars are examples. And so basically one thing also that I wanted to quickly talk about, you know, like in this field actually we are witnessing some paradigm shifts, right? So basically before we had, let's say, single task models that we have trained, let's say, CRF models, or like, let's say, SPM, or anything, like the single models. And then I would say starting from 2017, we came to the paradigm of fine-tuning. So basically we had language models that the fine-tuning for a specific task. So like it was, again, like I would say a single model, but with small variations to have for different tasks. So it's the fine-tuning paradigm. And now, I would say, since maybe 2022, 2023, we have like this paradigm of large language models, that these models become like single models for everything. And so we have GPT model and so on, but I have for marketing actually I have the Qatar model also. If you want to try the Qatar QA, can also try that the model as an Arabic century, I would say. And just to conclude, I wanted to also encourage you, I mean, if you are interested, we are actually, I think Dr. Ahmed also mentioned that there is a community, like I would say, Muslim ML community that is happening in all ML conferences. If you are interested to contribute, please reach out. Actually, like we are trying to, so before it was mostly, I would say, at Munich conference, but we are also trying to, inshallah, this year we will have it also at the USDLR. And so we are also looking forward, like, to the, I would say, community-based contributions. We are trying to have, I would say, GitHub organizations to have, like, share for the space, like anything that is related to Muslims, like the Islam, and also, like I would say, our community would like to have